Here's one more category of stoichiometry calculations. Now typically if you're doing a lab and a gas is produced, it's hard to actually collect that gas. You know, you think about some of the reactions that we've done where a gas is produced and you see fizzing and bubbling, but you don't physically collect that gas. Qualitatively, I know that a gas is produced. Or, for example, we even ran this first reaction in the lab. What volume of hydrogen gas will be produced when 2.5 grams of zinc react with an excess of hydrochloric acid? We did this. We took solid zinc, put it in a solution of HCl, hydrochloric acid. The zinc is +2, hydrogen +1, chlorine -1. So I get that single replacement. Or we'll kick out hydrogen, and by himself he's diatomic. We'll bring in zinc with chlorine, and then we check those charges. +2, -1, 2 chlorine, and it balances pretty slick, huh? 2 HCl, and we're done. So when we ran this one in the lab, we saw the fizzing and the bubbling. We knew a gas was produced. We were able to test the properties of the gas. It was a flammable gas, and it popped in that test tube when we had a lit wood splint. Hydrogen's kind of a cool gas, huh? But again, we didn't collect the gas. We didn't answer the question, how much hydrogen is produced. We just wanted to confirm that, yep, it's hydrogen. So often you measure a gas by its volume. How are you going to collect a gas and put it on the electronic balance? Seems kind of tricky. So there are different methods in the lab that we can use to measure the volume of a gas. We'll use a whole bunch of different kinds in the next few labs. So in this case, we should be able to calculate the volume of hydrogen I should produce, and then we can go in the lab and see if what we actually produce matches our calculations. When they say volume, we're probably going to measure in milliliters or liters. And so we start with what we have, 2.5 grams of zinc. We eventually want to know how much hydrogen is produced. It's a 1-to-1 ratio in the balanced equation, but it's not a 1-to-1 ratio of grams. If I have 2.5 grams of zinc, I don't get 2.5 grams of hydrogen. So we're going to cancel grams, 65.39 grams of zinc, and turn it into moles. The mass comes off my periodic table, and it's always the mass of 1 mole. Now here's where I could switch to any other substance in the reaction. I'd cancel what I have, moles of zinc, and I'd switch it to what I want, hydrogen. We're using the mole ratio in the balanced equation, which again, if I cancel my units, grams and grams, moles and moles, this multiply by 1, divide by 1 is not going to change my final numerical answer, but I like it because it keeps my units in check. Right now, if I end, I'd be at moles of hydrogen. If I go one further, I could cancel moles and switch it to grams. And if it's diatomic, we'd have to multiply the mass by 2. So hydrogen times 2 is about 2.02. The periodic table's mass is for 1 mole. Moles of hydrogen would be gone, and right now, if I plug it in my calculator, I'd have an answer in grams of hydrogen, which is fine, but again, it may be a little unrealistic if we're really going to run this. So we'll cancel grams of hydrogen and switch it to volume by using the density. The density will be given to you, and when we say the density is 0.0899 grams per liter, we mean that's the mass of 1 liter. Density is a ratio. It's a proportion of grams per volume. So we can cancel grams and turn it into liters by using the density. Now here's what people are always a little confused on. That 0.0899 is the mass of 1 liter. So the 1 goes on top and the 0.0899 goes on bottom. We're going to end up dividing by the mass. And sometimes density could be grams per milliliters, and then my final answer would be milliliters. This one we have liters. And so what do you know? We can cancel grams, and the unit that I'm left with is a volume unit, liters of hydrogen. So we plug it in. 2.5 divided by 65.39 times 1 divided by 1 times 2.02 divided by 0.0899 gives me, with maybe 2 sig figs, because my original was just 2, 0.86 liters of hydrogen. I promise this is as long as they're going to get. Where the last step is to use the density to convert between grams and a volume unit, liters or milliliters. Okay, so I would pause the video at this point. Try the second one with the mercury oxide, and then bring it back and let's see if we're getting these right. Alright, so here's this last one. Let's see what we got. How many liters of oxygen gas will be produced if 15 grams of mercury 2 oxide are decomposed? So we have our balanced equation. It's an easy one. Mercury 2 oxide is a plus 2 minus 1. Plus 2 minus 2, hello. So it's neutral. Elemental mercury is not diatomic, but the oxygen is. So we start with our 15 grams, which then we know we need to cancel grams. We'll put it into moles. So the 216, just the molar mass on the periodic table. Then we can use the ratio from the balanced equation to compare different particles. We'll cancel moles of magnesium oxide, switch it to moles of oxygen, using that 2-to-1 ratio from the balanced equation. If they asked me for moles, I would be done. If they asked for grams of oxygen, I could cancel moles and switch it to grams. This 32 is the mass of O2, diatomic oxygen, off my periodic table. And then finally, they give me a density. Density is grams per liter. So I can cancel grams and put the volume on top. And so I get it, like people flip this all the time. They feel like the 1.429 should somehow go on the top, but we're canceling grams. It's 1.429 grams for every 1 liter. We want liters, so that goes on the top. We multiply by any numbers on the top, divide by anything on the bottom. The original 15.0 was 3 sig figs, so I left it as 3.775 liters. If you start to feel comfortable with these stoichiometry calculations, you're in a really good place. It's all a method where I want to be able to use this ratio in the balanced equation to make my conversions. Now, if this is not doing so hot for you, then you're going to want to come in for a little help. Don't erase anything that you did that may be wrong, because then we can see what's right and what's wrong. We'll see where you're making your mistakes. But do come in if you feel like this is not going so well for you.